mechanical assembly line is designed to do exactly one thing. It processes identical blocks in a rigid, top-to-bottom sequence. But the moment a slightly different block arrives on the belt, the system doesn't adapt. It halts entirely. Early or highly basic programming operates on this same principle, executing instructions strictly line by line, from start to finish. That static execution model breaks down quickly. Software rarely operates in a vacuum. It has to respond to unpredictable user inputs, fluctuating datasets, and dynamic environments. A script that runs straight down the page cannot handle a user entering an incorrect password, or a shopping cart calculating variable tax rates. This diagram illustrates the solution: control flow. Control flow is the architectural mechanism that allows a program to dynamically route its execution path. Instead of a single track, the system evaluates logical true or false conditions to decide which set of instructions to run next. In C# software engineering, building these dynamic pathways relies on two core structural pillars. The first is decision-making, which creates branches in your code. The second is iteration, commonly known as looping, which repeats actions until a condition is met. Transitioning from writing rigid, linear scripts to building interactive state machines requires mastering these Boolean tools. By controlling the conditions, you control the machine. The foundational gatekeeper for decision-making in C# is the if statement. It exists to evaluate a single specific Boolean condition. If the condition is true, the code inside its block executes. If false, the program simply skips it. Looking at this split-screen diagram of a grade calculator, we can see exactly how this evaluation works. The execution block on the left only triggers because the comparison operator, in this case checking if the score is greater than or equal to 90, evaluates to true, routing the logic down the corresponding branch on the right. But we must account for failure. The else block serves as the necessary default fallback. It catches any state that fails the initial condition, ensuring the program always has a valid path forward even when the expected input isn't met. When we need to test more than a simple true or false, we expand this structure into an else-if ladder. This allows the system to sequentially evaluate multiple mutually exclusive conditions, like assigning a B, C, or D grade, stopping at the first true result it encounters. While if statements are powerful, they aren't the only tool for branching. When your software needs to route execution based on a single variable matching several specific values, C# offers an alternative architectural tool, the switch statement. This side-by-side comparison diagram highlights the structural intent of both tools. On the left, the else-if ladder is busy evaluating mathematical ranges. On the right, the switch statement is strictly evaluating discrete, exact cases. If statements are engineered for complex logic. Whenever you need to use logical operators like and, or, and not, or evaluate broad numerical ranges, the if structure is the required tool. Switch statements, however, bypass complex range evaluation entirely. They favor highly optimized exact value matching. The program takes one variable, finds the exact matching case, and executes it immediately. Because of this exact matching, switch statements are the optimal choice for specific use cases: routing an ATM menu, processing day and month selections, or categorizing discrete employee departments. Selecting a conditional structure defines how the system will evaluate its data, categorizing inputs into either flexible ranges or exact predefined values. Branching handles decisions, but software also requires cyclical repetition. This brings us to loops, engines of iteration designed to automate repetitive tasks without writing the same line of code 1,000 times. A loop executes a specific block of code repeatedly. It continues the cycle endlessly until a bounding condition becomes false, at which point the machine stops iterating and moves on to the next task.
This animated diagram models a while loop as a precondition execution engine. Notice that the condition evaluation acts as a toll booth located explicitly before the code block is entered. The consequence of this structure is absolute. If the initial state is false, the toll booth stays closed. A while loop may execute 0 times. By contrast, this updated diagram models a do-while loop. It is the structural inverse. The evaluation toll booth is shifted to the end of the iteration, after the code block has already run. This structural shift guarantees that the code block will execute a minimum of 1 time, regardless of whether the initial condition is true or false. Consider prompting a user for a password. You must ask them to input their credentials at least once before you can validate if those credentials are correct. A do-while loop is built exactly for this scenario. Selecting a loop type solves a specific architectural problem. You choose while when you must validate the state before taking action, and do while when baseline execution is required prior to validation. When the exact number of required iterations is known in advance, like processing exactly 100 entries in a ledger, we turn to the for loop. This diagram tears down the syntax of a for loop into its three internal components. First, the initialization sets the starting point. Second, the condition determines how long the loop runs. Third, the increment counter updates the value with each cycle, automatically tracking our progress. C# also provides the foreach loop. Unlike the for loop, it removes the manual index tracking entirely. It serves a highly specialized role, sequentially traversing arrays and collections, guaranteeing that every item is processed exactly once without the risk of an off-by-one error. But autonomous cycles aren't always enough. Developers need tools to manually override or abort a loop's natural cycle based on real-time events. In this 5-step loop sequence diagram, we see how the break statement functions. Triggered here on step 3, the break command terminates the loop cycle. It cancels all remaining iterations and exits the structure, moving the program execution to the next block of code. Using the same 5-step sequence diagram, we introduce the continue statement as a surgical override tool. Triggering continue on step 3 doesn't destroy the loop. It aborts the current iteration, skipping the remaining block, and instantly jumps to step 4's evaluation. Manual overrides like break and continue act as essential safety valves. They prevent redundant processing once a target is found and stop fatal infinite loops, ensuring system efficiency. To prove how these discrete control structures combine to build a cohesive application, let's reverse engineer the logic of a complex interactive system, an ATM terminal. This hierarchical diagram maps the architecture of an ATM program. Notice the outermost layer. It relies on a continuous while loop to sustain the session, ensuring the terminal stays active and ready between different users. Moving one layer down, the system must route the user's input, whether they want to check their balance, deposit funds, or withdraw cash. This routing is handled cleanly by a nested switch statement. Because the menu options are discrete, exact values, the switch instantly matches the user's choice to the correct internal feature. Zooming entirely into the withdrawal case of that switch, we find the final validation layer. Foundational if-else blocks compare the requested withdrawal amount against the current account balance, ensuring the transaction is mathematically valid before dispensing cash. This system reflects definitive C# best practices in action. Isolate logic with simple conditions, apply switch statements for menus, and bound iterations strictly with the correct loop variant. Advanced software is simply an orchestration of these foundational elements. By mastering branching and iteration, you acquire the precise engineering grammar required to build robust, scalable applications in C#.